Hi there, this is an introduction to Verilog, recording on introduction to Verilog. These are some of the topics we'll be covering. Brief introduction along with simulation of the example code. This topics will be covering what a module is, how to instantiate a module, how to use and override parameters using delays within code, procedural blocks, data types, operators, control statements, and blocking and non-blocking assignments. So Verilog is a programming language, but meant for hardware design. So it's called an HDL, hardware description language, very similar to other programming languages, very similar constructs, syntax, but there are some key differences. So what's a Verilog module? It's a basic building block within Verilog language. So it can contain a very simple design, or it could even contain a subsystem or a complete system. So any complexity is possible within a module. Hierarchical designs contain modules with instantiated modules, similar to like a parent and child hierarchy. So a module can contain many other instantiated modules, objects of other modules. So structure of a module, this is how a structure of a module is like. So you have these words in blue, which are the Verilog keywords. So you have a module, and for every module you have to have an end module at the end, indicating that that's where the code finishes. You can put comment at the end saying, if it's a really large module, that's the end of a certain module. So you will have a port list. Port list is an interface of a module to the other external world. So after the port list, you will have to describe your inputs, which out of those port lists are the inputs, what are the outputs, their directions, types. We'll talk about the types in a while, their sizes, and of course their names. So size, it could be a single bit, it could be a multi-bit bus. You must be, we have processors which are 16-bit, 32-bit, 64-bit, so that's where size comes in. Then after the ports, we go for declare any internal signals. If you have to initialize, we do that. If we have any instantiated modules, like any child module, they are instantiated there. We may override certain parameters of those modules if needed, and then the body of the code itself. So that's how, in a nutshell, a structure of a module looks like. So now here's the code we have. This is a 1-bit full adder. So let me show you how a full adder looks like. So this is a 1-bit full adder diagram. This is a truth table. You can see there are two XOR gates, 2 AND gates, and 1 OR gate. So this is a truth table. You must be familiar with this one. You have A input, B input, the carry input, and then you have the sum output and the carry out. And later on, we'll use this 1-bit adder to create a 4-bit adder. Let's go back to the code. So it's a structural code. Structural code uses gates and instances of other modules, and so again, the 1-bit adder has this is the port list, and this is where we are describing which one of those ports are inputs and outputs. Since no size is mentioned, so that means it's a single bit size, and that's why, like the code, the comment at the top says it's a 1-bit adder. So we have 3 inputs and 2 outputs. So this code, structural code, has been used with the pre-built which are provided in Verilog compilers, gates like XOR, AND gates, and OR gates, like I showed you in that diagram. Behavioral code is at a higher level, and as you can see, this one single line is doing the same thing which we are doing here in multiple lines. But I think in your labs, you'll be using structural code, at least during the initial labs. Maybe at the later on stages, you might be moving on to behavioral code. So that's like I was showing in the slides. This is how a module is. created, defined. So you have module, and then you have end module at the end. Now what we are doing further in this design is, in this code is, we are extending this 1-bit adder to and converting it into a 4-bit adder. Verilog allows that when you have instances of this type, and when you create an module of this type, and when you create an instance of it, you can, where possible, you can use parameters like a size, like we are doing here, and convert this into a 4-bit adder. So this is a 4-bit adder. So again, similar methodology. We declare the port list. Here we have to define the size, parameter size, and then we define which ones are our inputs, outputs, their sizes, their names, and these are the internal signals and instances. So why we have these internal signals? Because we are going from a single bit adder to a 4-bit adder, we need some internal carry ins and carry outs. If you go back to that diagram here, so the carry out of this adder becomes the carry in of the next one, and so that's like in a chain fashion. So that's what we are doing in the code here. So the first carry in is C in, which is coming from the top, and the last carry out is the carry out of the last internal signal, and the other ones are interconnections. So again, module, that's how we do a module. And now at the very top level, we have a test bench. Now look, I hope you see that there's no port list here. And that's because a test bench does not require a port list, unlike the modules. The test bench is meant only for simulation, whereas these modules are hardware modules, so they have to have ports for inputs and outputs, whereas a test bench usually encapsulates. It's like a wrapper around your DUT. So our DUT is this adder now, 4-bit adder. And so this is the 4-bit adder, and once again I can actually override the size of this 4-bit adder and convert it to a 5-bit adder, even a 32-bit adder if I wanted. So this is again possible. I just use this define parameter keyword and change this parameter size in the instance my adder, which was originally 4. We changed that to 5. So that's how we create modules and a simple test bench around that. So let's now run our that parameter code I was showing you, parameterized adder, this file. I have already copied that over to the red machine. So to compile this code, which is the same code which I was showing you there, we use this command Verilog, and then we define the output where we want to capture the outputs from the test bench, and so that we know how the results are, if our design is behaving as we expect. So let's call it anything, parameterized adder.o, and then we mention the name of the Verilog file. So now Verilog has compiled that, and the outputs from that test bench and the modules under it have been captured in that file. So to see the outputs, let's do this command, and let's see. Yeah, so it's a 5-bit adder. So let's see, and I have converted the result in digital format so that it is easier to read from the original binary format. So you can see A is 4, B is 1, C carry in is 0, so the output sum is 5. Here you have 13 and 13, then the sum is 26. Here we have a case carry in is 1, this is B is 6, so that's 7 plus 25, 32. So carry out is 1. Because it's a 5-bit adder, so this is basically means 2 raised to the power 5. So this is 32 and this is 0. So same result here. And another one with similar is here. This is 29 plus 130 plus 22. So that's 30 plus 22 is 52. And then again, here you have 1 and 20. So 32 plus 20, again 52. So the adder is expecting as we is behaving as we expected. So next we are talking about using delays in Verilog language. Delays are useful for accurately modeling the behavior of your design. Any hardware devices, they will have inertial delays, propagation delays due to the hardware components, interconnecting delays of the nets. So those can be modeled using delays. The delays are very useful for simulation purposes, like we did in our test bench. I will just go over that briefly again with you. That is for applying signals at appropriate time and for generating clocks, also known as the test bench stimulus. So this is example code of using delay. Like here I have an always block, and every 10 time units I toggle the clock. So clock, whatever the original value of clock is, if it was 1 or 0, this is the opposite of that. So the period of clock would be 20 time units. So because every 20 time units will have a 1 period of the clock. Here another example. I wait for 5 time units. Typically the time units are in nanoseconds. I will show you that in the next slide. And then we wait for 5 time units and then assign the following signals. So again, using the example of that adder. So a test bench, which is a input to the adder, is a random value after this delay of this many time units, and so on. Important note is that delays cannot be converted to hardware. So whereas the language, our adders, the 4-bit adders that we were using, single-bit adder, they will be getting converted into hardware, but the delays do not. They are only good for simulation purposes or for modeling, our design when we are just trying to model the design of a hardware. So here you can see I have an initial block, and this is the beginning of the block, and this is the procedural block, they are called. And so I use some display statements. This is to, they go to the output file, which I had showed you on the red machine. And then I have a repeat loop. I do I repeat the code within this repeat loop 8 times. And so I capture the values of a test bench, which I assign here in random. So this initial block and this initial block run in parallel. And so whatever the values of a test bench, B test bench, I capture those. And since I'm using a decimal format, that's why the result was showing up in decimal there. And I use unsigned because binary numbers can be signed or unsigned. So now we're going to talk about procedural blocks. They contain procedural statements which are executed sequentially, very similar to other programming languages. The code in the block is run when the signals in the sensitivity list change. So there are 2 types of procedural blocks. Initial block, which I just showed you in that test bench also, run only once, doesn't require any sensitivity list. Delays are usually used typically for initializing signal values and in test benches like you saw there. Always block, it contains a sensitivity list. When it does not contain a sensitivity list, it must use delays. Like again, I think there was a code, or I will show you another code where we have a always block without a sensitivity list, and then we use delays there. So this is a sensitivity list, and anytime these signals peak clock or reset change, the code is run accordingly, whether it was a reset which was low or a peak clock rising edge or pause edge of peak clock occurred. So this code would run when the signal in the sensitivity list change, e.g. every peak clock. So here's another code. This code is for a D flip-flop, which is a sequential element. We have an always block here. This is a part of a module. So it is module and module. Module is the D flip-flop. We have the parameters, port, their sizes, etc., like I described earlier. When we don't have a data type, like this one has Q is of type reg, whereas QB is wire by default. So I'll talk a little more about reg and wire little in a while. So here, this always block, you can see we run it on every pause edge of the clock or neg edge of the reset. So when there's a reset is low and the neg edge has occurred and it is low, so it's an asynchronous signal, and asynchronous low active reset, so Q will be asserted to be low. Otherwise, synchronously, that's why this is called a synchronous circuit. Synchronous to the clock, pause edge of the clock, Q will become whatever the value of D is. In between, when the between one edge to the other edge, Q will just hold the value of D, which was there, till D changes on the next edge or the following edge. So here's an always block, but I don't have a sensitivity list, but I am using delay there. When we don't use delay like this without a sensitivity block, this will become an infinite loop and your simulator will get held up. So this would give a clock of 8 time units, 8 nanoseconds. Why 8 nanoseconds? Because here we have a time scale. This is a time unit and this is a resolution for the simulator, which we run like Verilog or any other simulator. So another always block, again without sensitivity list. These are typically used within test benches. In hardware, we usually have a sensitivity list of this type. And then it's a test bench without ports, like I described, some size parameter which I'm overriding. So instead of size 1 D flip-flop, I'm making it into a size 4 D flip-flop. And then I'm just instantiating it and thus supplying some test stimulus here using for loops inside the initial block there. So again, the D flip-flop file has also been copied over to the red machine. So let's run this. And again, the syntax is the same, Verilog, the output file where we want to capture the outputs. Let's call it D flip-flop out.o and name of the file. So Verilog has captured all the output from our top level test bench, which was in that file, and it obviously had a D flip-flop hardware module also in it. So let's run this, see what the outputs look like. So again, to do that, the command is vvp and the output file name. So here I've captured in these columns data in, clock, and Q out. QB out is just the opposite of Q out. So you can see when the clock edge happens, when the rising edge of the clock happens, 1, whatever is the value of D before that, that becomes the value of Q. Again, here D was 3 before the edge came, and Q becomes, it was 13, Q became 13. Here, when the edge came, D was 10, and Q became 10. In this test bench, which I wrote, I've also captured here. I've captured a VCD file, this one, to view it using this waveform viewer. This is also helpful. So let's see how does it look like. So we go there. To do that, what we have to do is GTKWave and the name of the file. I think it is dump. Yeah, this one. So we type that, and it opens a waveform viewer where you can actually see the signals. Yeah, it's opened up here. So the signals are captured there. We insert them, say yes please, and we zoom out. And now you can see this is a clock edge, this is a D in. So we're on the edge. When the rising edge comes, whatever is the value of D becomes Q. And here it was D, so it became D. On the next edge it was still D, so it did not change, stayed there. and so on. Here becomes from, it was C, and so on. You can see that. So in between, whatever is the value of D, it does not matter. So this type of element is called a sequential element, because they hold their value, like you can see between this edge to this edge, they hold the value even though the input is changing. So this is how they are different from combinational logic, which would change. Combinational logic would change right away with some delays, of course, once the input change. So next we talk about data types. There are three main data types for using in the code of body of your code, or for signals and variables ports. Net is one of the types. It defines represent the physical connection between two signals or two ports, input and output ports from one module. Could be, if they were to be connected to one input to the output of the other one. So wire is the most common subtype of this net type. And when we use wire signals, we have to assign values to that. We use the assign statement. Variable is another type, and reg and integer are the two common subtypes. They are used for assigning or driving signals within the procedural blocks, the initial and the always block. Event is the third data type. It's a type of timing control, just like delay is also a type of timing control, but this one is most of the events are synthesizable, and they represent change of value on a net or a register, like we saw in that always block, always at the pause edge of the clock. So, and it uses a symbol, that at symbol. So we have to, when we use within those always block, which is a part of a procedural block. So when we want to assign or drive a signal within that procedural block, it has to be declared as of type reg. Must be of type reg. Okay, so next operators. They are very similar to like those in the C language. We have logical operators. We have equality and comparator operators, bitwise operators, and of course we have arithmetic, reduction operators, and some miscellaneous operators. Control statements. Verilog also has control statements like most other programming languages, and there are if, else, if, nested if statements, they are allowed. So that's example, they go inside these statements, control statements, they go inside procedural blocks, initial or the always block. Then there's a case statement, again similar to C language, and then we have loops like while loop, for loop, and repeat loop. I showed you some of these in that test bench. We were using some of these in the test bench. Like here in the D flip-flop test bench for the D flip-flop, inside the initial block I have this for loop. I do 32 times. I wait 2 time units and then assign a random value to data input, which is going to the D input of the D flip-flop. So this is the last section of the block, of our this brief short tutorial. Blocking and non-blocking assignments. They are used within procedural blocks. Use the blocking assignments, which is this symbol, for modeling combinational logic. That is logic which is based on gates, AND gates, OR gates, etc. No sequential logic for using the blocking. So don't use sequential logic when you're trying to design sequential logic. Assignment takes place right away. That is, it blocks any trailing assignments from taking place until this current assignment has been completed. So it is known as a single step assignment. That is, the right hand side is evaluated and the left hand side is updated right away. The non-blocking assignment, the symbol is this. This is used for modeling sequential logic which holds its values like the D flip-flops I showed you there. It's known as a two-step assignment. The right-hand side is evaluated at the start of the event, e.g. a clock edge, but the left-hand side is assigned after the event is over, or you can say or at the end of the procedural block. So as a rule, in the initial block, which is a procedural block, use this assignments only, and in the always block, use one of the two assignments, only one of the two assignments. Don't mix them within one block, and depending upon what you are trying to model, whether you're going for combinational logic using gates or sequential logic using flip-flops. So here's an example code. It's like a kind of like a test bench. That's why there are no ports. So I just have internal signals called clock, ABC, KLM, and then I have initial, initial block here, just basically to initialize the values of ABC. This is called concatenation of signals. So you can group signals which are declared separately, and you can see they're all of type reg because I'm using them, assigning them within the procedural block. So assign same value to both ABC and KLM, and just after waiting for 50 times units, I just finished the simulation. And what happens at the same time when the initial block runs? I just have a clock which is 10 time units. You can see after 5 time units I change the value, and in between I capture the values of ABC, KLM, and the edge of clock. And this is the code which is to show you the difference between when we use blocking statements or versus non-blocking statements. So again, I have the code copied over to the red machine. So let me go to the red machine, and the code is there in a blocking, non-blocking state. So let's run this code using the same Verilog output, blocking, non-blocking, blocking, non-blocking, and the name of the file is this one. So I did this command, which is here. You can see Verilog and define the output type, and it has been captured, created and captured. The output has been captured. So let's see what the output looks like. So we do this, VP, and name of the output file. And now you can see ABC were initially same as KLM, like we had initialized, but you see, unlike KLM, where the one value is getting shifted every clock edge, ABC became 0, and it just stays 0 once it becomes 0. So this is the main difference between the two type of assignments, because one of them is a single step and the other one is a two-step assignment. So here we ABC was initially 1, 0, 0. So C was 0, so A became 0. So when A became 0, B became 0. And then when B became 0, C became 0. So after first clock edge, the A, B, C, they all turned 0, and then they just stayed 0. But here at the clock edge, KLM were initially 1, 0, 0. So K became 0, but L became 1 because K's value was 1. And this all updating happens once we are at the end of, or like I had mentioned, once the event is over. So all those assignments happen once we are here at this point of time. They don't happen right away. So that's why this is a two-step assignment and this is a single-step assignment. And that's the key difference between these two. So you have to be careful, and like I showed in the slides, follow these rules and you'll be fine. For combinational logic, use these assignments, and for the sequential one, these non-blocking ones. That's it. Thanks a lot for your time. I hope you find this useful.